Hi boys and girls, this is lecture 4.8 in Unit 4, the topic, Newton's method. Newton's method is a technique for approximating real zeros of a function using tangent lines. This is how it works. Consider a function f that is continuous on the interval ab and differentiable on the interval ab. If f of a and f of b differ in sign, then by the intermediate value theorem, f must have at least one zero in the interval ab. Let's take a look at this diagram. The red curve here is our function, and on the interval that we've chosen, a, b, we can see that it's continuous and differentiable. Furthermore, at the left endpoint of the interval a, we can see that the function value is negative here. Some function value, we don't know exactly what it is, but it's negative. And at the right endpoint of our interval b, we can see that the function value on the curve is a positive number. We don't know exactly what that number is, but we do know it's positive. Therefore, by the intermediate value theorem, we know that to get from this negative number to this positive number on a continuous and differentiable function, we had to go through every value between this one, and of course in this case that includes 0. So now we know, even though we don't know exactly what it is, that there is a 0 between a and b on this curve. So let's find this 0 using Newton's method for approximating zeros of a function. Suppose you estimate this 0 to occur at some x sub 0 in the interval ab. You know what a is, you know what b is, you know that there is a 0 on the curve somewhere between a and b, so you're going to choose a value between a and b as a guess. I'll call this x sub 0. Of course, once you have x sub 0, you would easily be able to calculate the function value there, giving you an ordered pair, x sub 0, comma, f of x sub 0. Furthermore, with the first derivative, you would be able to calculate the slope at that point as well. With a point and a slope, you could write an equation of a tangent line at that point. Newton's method is based on the assumption that the graph of f and the tangent line at x sub 0, f of x sub 0, both cross the x-axis at about the same point. So notice this blue line is representing the tangent line at x sub 0, f of x sub 0. Newton's method is making this assumption that where this blue line is crossing the x-axis at the point x sub 1 is really close to where the actual curve is crossing the x-axis. So this first x sub 1, which is the x-intercept of the tangent line, is an approximation of the 0. But we don't stop there. Now we say, let's take x sub 1 as a new guess for an approximation for the 0. Let's find the function value there at x sub 1, comma, f of x sub 1. Let's use the first derivative to find the slope at that x value, and then write an equation of a tangent line at that point. You can see the x-intercept of this tangent line here at x sub 2 is even closer to the actual 0. So we could continue this method, again taking x sub 2, finding the point there, the slope there, writing an equation of a tangent line, getting closer and closer to the actual 0 of our function. Since you can easily calculate the x-intercept for these tangent lines, you can use them as second or third or fourth and usually better estimates for the 0 of f. So that's how this works. Let's do an example. Okay, here's our plan of action. Let f of c equal 0, where f is differentiable on an open interval containing c. Then, to approximate c, the place where the curve is crossing the x-axis, use the following steps. Number 1, make an initial estimate or guess x sub 1 that is close to c, the actual 0 of the function. A graph is definitely helpful. Number 2, determine a new approximation. Remember, this first approximation was just your initial guess. We're going to use Newton's method to find a closer approximation. This can be done by taking your initial guess and subtracting the function value at that x over the first derivative at that x. That is going to give you a new better approximation. Third, if the difference between your initial guess and the new approximation is within the desired accuracy, then let that new approximation serve as the final approximation. Otherwise, return to step 2 and calculate a new approximation. Each successive application of this procedure is called an iteration. Calculate 3 iterations of Newton's method to approximate a zero of f of x equals x squared minus 2. Use x sub 1 equals 1 as the initial guess. Good news, this is all calculator work. Notice that I have a graph of the curve here. Here is the actual zero, and we're letting 1 be our initial guess, x sub 1. That means the function value at x sub 1 here is x sub 1, comma, f of x sub 1. Using that function value and the slope at that point, you can see the tangent line crosses the x-axis here, closer to the actual zero than our initial guess. Using 3 iterations of this process, we will get an approximation of the zero that's very close to the actual zero. Let's first of all discuss what the actual zero would be. If we set 0 equal to x squared minus 2, you can see that means 2 equals x squared. When taking the square root, we get plus or minus the square root of 2. So since we're on the positive side of the y-axis, we know that we're looking at the actual value of the zero is the square root of 2, which is approximately 1.414. Let's see how close to this Newton's method gets us. We are going to need our first derivative for this process, so let's go ahead and calculate that. F prime of x for this function is 2x. Now, our first guess is 1. The function value at 1 is -1. Notice I just plug it back into the original function. And then the first derivative at 1 is 2 times 1, which is 2. Therefore, my first approximation can be calculated this way. The initial guess minus the function value over the first derivative at that guess. Since 1 minus a negative half becomes 1 plus 1/2, then my first approximation is 3/2. You can see that that looks like where our tangent line is crossing the x-axis. But we're going to do 3 iterations of this process. So now we take 3/2 and let that be our next x sub n. We would need the function value at 3/2, which is 1/4. Let your calculator get these values for you. The first derivative at 3/2 is 3, and then we'll calculate our next approximation by taking 3/2 minus the function value at 3/2, which is 1/4, over the first derivative at 3/2, which is 3, and this comes out to be, I'll just write down the decimal, 1.416. Then we do our third iteration using this value as our next x sub n. Function value at 1.416 is 0.0069. We'll just say it's about that. The first derivative at 1.416 is 2.833 approximately. And then calculating the new approximation, we're going to get 1.414216. Now, since we've done 3 iterations of this process, we're done here. This will be our final approximation for this problem. Look how close it is to the original, or to the actual zero. A better approximation of the square root of 2 is 1.414214. So just 3 iterations of Newton's method got us an approximation very close to the actual zero. This is still kind of bothering me that these do not look like 4. So just in case we're confused, this is 1.414216. Oh yes, that's much more clear. In this last example, we're going to use Newton's method to approximate the zeros of f of x equals 2x cubed plus x squared minus x plus 1. Continue the iterations until 2 successive approximations differ by less than 1/10,000th. So in this problem, they're not telling us how many iterations they want us to complete, and they're not giving us the initial first guess. Instead, they want us to come up with a reasonable first guess based on the graph of the function, and they want us to continue the process until we find that two successive approximations are so close that they differ by less than 1/10,000th. So I'm not sure where this little mark came from, but let's get rid of it. So let's come up with our reasonable first guess by examining the graph. Here is the actual zero of the function. Therefore, I'm going to choose as my first guess negative 1.2. I'll need the function value at negative 1.2 as well as the first derivative at negative 1.2. So let's calculate the first derivative. F prime of x will be 6x squared plus 2x minus 1. Therefore, each approximation will be found by taking my x sub n value and subtracting the function value there over the first derivative there. So let's fill in some of these values. Remember to let your calculator do the work in finding these function values and first derivative values. The function value at negative 1.2 is 0.184. The first derivative at negative 1.2 is 5.24. Therefore, my first approximation will be negative 1.2 minus 0.184 over 5.24, and that is negative 1.23511. We're going to use this approximation as our next x sub n, negative 1.23511. The function value there is negative 0.00771. The first derivative there, 5.68276. And then the second approximation is going to be negative 1.23375. Now let's examine these two approximations. Remember, we want them to be so close that they differ by less than 1/10,000th. Well, here is the 10,000ths place. We can see that they differ by more than 1/10,000th. So we need to do another iteration of this process using this approximation as our next x sub n, negative 1.23375. Our function value here is 0.00001. Notice how close this is to 0. Our first derivative here, 5.66533. And our next approximation then is negative 1.23375. Let's examine these two approximations. Again, we want them so close that they differ by less than 1/10,000th. Well, since they are exactly the same and the numbers in the 10,000ths place are exactly the same, we see that they are so close that they differ by less than 1/10,000th. So we can stop here, and this can be our final approximation for this problem. That's it for today's lecture. As for the picture on this final slide, come on, boys and girls, you know I had to. Look at this cute little math book made out of a fig Newton, this calculator made out of, I don't even know what that is, and this cute little apple. Go make some cupcakes. God bless you, boys and girls.